All right, question 5 says to evaluate the line integral of the vector field f over the curve C by evaluating the corresponding surface integral in Stokes' theorem with an appropriate choice of surface S. Part A, our vector field f is 2y, comma, negative z, comma, x, and C is the circle x squared plus y squared is equal to 12 in the xy plane with counterclockwise orientation when viewed from above. Okay, so here is our circle. Its radius is the square root of 12 and it's oriented counterclockwise. And so I want this to be the boundary of some surface. Okay, so to make things simple, I'm just going to choose for the surface to be this flat disk that's enclosed by the circle that lies in the xy plane. Okay, so that's our choice of surface there. Now I'm going to go ahead and compute the curl of our vector field because I'm going to need that for the surface integral. And so the curl here is a constant vector. It's just 1, negative 2. And since I'm choosing S to be this flat disk in the xy plane, the unit normal vector at all points is going to just simply be k, not negative k. Notice that since the boundary curve is oriented counterclockwise, if I curl my right fingers in the positive direction for C, then my right thumb will be pointing upwards. So I want to choose the unit normal n to be positive k there. And since the curl is a constant vector and the unit normal vector is also a constant vector, I'm just going to take their dot product here, which is just negative 2. And so when I look at this surface integral here, I'm just going to be integrating this constant of negative 2. Okay, so altogether now, Stokes' theorem says that this line integral, which is really what the question is asking us to compute, is equal to this surface integral of our curl, and this dot product is negative 2. And so this boils down to just integrating negative 2 over this flat disk here. So that's just going to be negative 2 times the area of that disk. And since the disk has radius root 12, that's going to be negative 2 times pi times the square root of 12 squared. So that's equal to negative 24 pi. All right, cool. That's pretty nice. Let's go ahead now and look at part B. So here, our vector field f is 2xy sine zi plus x squared sine zj plus x squared y cosine zk. And C here is the boundary of the plane z is equal to 8 minus 2x minus 4y in the first octant with counterclockwise orientation when looking towards the origin. Okay, so our curve C here is the curve in blue. And for the choice of surface S, again, I'm just going to make this as simple on myself as possible. I'm just going to choose S to be the portion of this plane that lies in the first octant, right? What I need is that this blue path is going to be the boundary of whatever surface I choose, right? And so I'm just going to choose this thing that's enclosed by this triangle. And so as far as the orientation goes, again, it says the curve C is oriented counterclockwise when looking towards the origin. So if we're standing, out here in the first octant, looking towards the origin, I see this counterclockwise orientation. So that would imply that our surface S will have, for its normal vector direction, right, the normal vector will be pointing outward here into the first octant to follow the right-hand rule convention. All right, so now let's go ahead and compute the curl of the vector field. And when you do this very nicely, you find that the curl is just 0. Okay, so Stokes' theorem then implies immediately that the line integral over this path C is equal to, well, the surface integral of the curl of our vector field. But since that's 0, then the line integral is equal to 0. Okay, now a comment here in relation to the last video. Another way we could have argued this, once we now know that the curl is 0, and we note that the domain of this vector field is all of R3, right, which is open, connected, and simply connected, then we know from the big theorem on conservative vector fields, right, that the curl vanishing everywhere says that this thing is a conservative vector field. And so that implies, right, that the circulation over any simple closed curve C in R3 is equal to 0. So in particular, it'll be 0 over this simple closed curve. All right, cool. So now for the last part, all right, so we're looking at the vector field f, which is x squared minus z squared, comma y, comma 2xz. And c here is the boundary of the plane. Z is equal to 4 minus x minus y in the first octant with counterclockwise orientation when looking towards the origin. Okay, so pretty similar curve here that we saw in part B, right? So again, I'm just going to choose for my surface to be the portion of this plane in the first octant. Okay, so in other words, just the surface enclosed by this triangle formed by our boundary path. Okay, and since I have this counterclockwise orientation on the blue curve for this surface, then I need an outward pointing normal there to follow the right-hand rule convention. All right, so let's go ahead and compute the curl. Okay, not too bad. Here we get 0, comma, negative 4z, comma, 0. And for the surface, well, since the plane's given in explicit form, z is equal to 4 minus x minus y, I'll just go ahead and use an explicit parameterization for the surface. So r of xy is x, comma, y, comma, 4 minus x minus y, where here we're going to let x, y vary over this region R, which is just going to be the projection of our surface onto the xy plane, which is just this triangular region you see here bounded by this blue line, which is just this blue line right here, right? It's just the plane intersecting the xy plane. All right, now for the normal vector to the surface, according to the table, right, from the surface integrals worksheet, this is just minus gx minus gy1, where g of xy is 4 minus x minus y. So that comes out to be 1, 1, 1. And so one thing we've got to make sure to check is that, hey, is this thing pointing outward? And the answer is yes, 1, 1, 1 points outward. So we have the correct orientation there for the surface. One other comment, though, is that since we are looking at a plane for our surface S, the normal vector could also have been found by just rewriting this equation as x plus y plus z is equal to 4. And we know that for a plane, we can read the normal vector as just the coefficients of x, y, and z. So 1, 1, 1. There you go. That's another way to see that. All right, cool. So now let's go ahead and compute the integral. Okay, so the line integral, according to Stokes, is equal to this surface integral of the curl of our vector field. And so to compute this using this parameterization, we're going to integrate over this triangle in the xy plane, and we have to take our curl vector and evaluate that along our surface S. That's what this portion is doing. And then we're going to dot that with this normal vector. All right, so now for the curl vector evaluated along the surface. Okay, here, well, we're setting x to itself, y to itself, but z is equal to 4 minus x minus y. And since our j component for the curl vector is negative 4z, okay, this, when we put this in for the integrand, is going to become negative 4z, right? And z is 4 minus x minus y as we move along the surface. Okay, so that's this portion, and then we're dotting that with the normal vector, 1, 1, 1. All right, and so we're going to go ahead and take that dot product. That's just going to give us the negative 4 times 4 minus x minus y, and I would just put the negative 4 out in front. And we're integrating over this triangle, and so I'll go ahead and just fill out the triangle using vertical strips. So for one of these strips, y will vary from 0 up to the blue line, where y is 4 minus x. So those are the y bounds. And then for the x bounds, we're going to stack those vertical strips from 0 to 4. Okay, so I'm going to leave the rest of the details of the integral to you, but you wind up getting minus 128 divided by 3 for the value of that integral. So that is our line integral according to Stokes theorem. All right, great. Well, that is going to do it. Thanks so much.